A semiconductor is a material that imparts current, but only partially. Its conductivity lies between a conductor, which has full conductivity, and an insulator, which has negligible conductivity. Your computer, or the beloved smartphone on which you may be watching this right now, is actually empowered by a bed of silicon covered with billions of transistors thinner than a strand of hair, composed of a solid substance called a semiconductor. Any crystal is comprised of atoms that accommodate electrons in a large number of closely spaced energy levels. However, according to Pauli's exclusion principle, the proof of which goes beyond the scope of this video, demands that only two electrons spinning in opposite directions can harbor a single energy level, making it truly stable. These levels can be represented by lines separated by small distances where electrons are permitted to be located in these particular levels only. A few energy levels are then grouped together to form bands known as energy bands. The energy band on the screen has the least amount of energy and is termed the valence band, while the energy band above it has a higher energy level and is the conduction band. The energy required for an electron to jump this distance is called the band gap energy. So here's the band gap that you see. The first crystal diagram has an odd number of electrons in its valence band, and no electrons in the next band, which makes for a single loose electron in its highest energy level. This will readily flow to the conduction band when given a small kick or connected to a battery, providing a huge current. This crystal is a conductor. Examples of conductors are metals, such as copper and iron. The electrons in the second crystal are not only very stable and tied to each other, but there is also a pair of electrons in its conduction band too, thus making the flow of electrons to the conduction band nearly impossible. This represents an insulator. Paper, rubber, and glass are some common insulators. The third crystal has a loose electron, but not an empty conduction band. However, it does contain half-filled energy levels that can accommodate more electrons. This loose electron can be projected to the conduction band when given a strong enough kick, rendering a small amount of current. This crystal is a semiconductor. Major examples are silicon and germanium. This operation can be summarized by a drawbridge analogy, where the bridges representing conductors either overlap or join so that passengers can easily cross. Semiconductors can be represented by a poorly constructed bridge that only closes halfway and requires a passenger to jump the distance between them. Finally, an insulator is a bridge that does not close at all, making it impossible for any passenger to leap and reach the other side. The ability to permit the flow of electrons through a substance is its conductivity. The conductivity of conductors is highest, while it is lowest for an insulator, as the electrons flowing through it are negligible. However, as the name suggests, the conductivity of a semiconductor is moderate. Another interesting thing about a semiconductor is that the current is carried not only by electrons, but by the vacancies they leave behind, which are known as holes. The holes left behind in the valence band can be occupied by electrons from lower states and contribute to the flow of current, thereby leaving a hole in these deeper states as well, which will be occupied by electrons beneath, and so on. The current can thus be defined as the rate of flow of these positive charges. To contemplate its utility, one must understand that the current flowing through a semiconductor, unlike a conductor, is not an uncontrollable surge of electrons, but rather a delicate combination of charges and their steady flow. Innovative engineering put forward the idea of contaminating a silicon or germanium atom on purpose to induce new energy levels. Materials are contaminated with either crystals that contain more valence electrons than a semiconductor, usually phosphorus, which tend to roam freely in the structure and contribute to the flow of electricity, or with crystals containing fewer electrons, aluminum, which borrow electrons from silicon and leave behind extra holes. The contaminated silicon resulting from the sprinkling of phosphorus is called an N-type semiconductor, and the resulting silicon from the latter process is called a P-type semiconductor. The amount of contamination or doping provides the means of controlling current. So this is the equation, the Fermi Dirac equation, and it's based on the probability that a particle will have energy E here. So at absolute zero, fermions will fill up all available energy states below an energy level EF called the Fermi energy with one and only one particle. They are constrained by the Pauli exclusion principle at higher temperatures, and some are elevated to levels above the Fermi level. For low temperatures, these energy states below the Fermi energy have a probability of essentially 1, and those above the Fermi energy essentially 0. The quantum difference, which arises from the fact that these particles are indistinguishable. So what this tells us is that the energy is not available for those electrons to jump in the semiconductor when the temperature is low. As temperature increases, as we see with usage in our electronic devices, our phone, our calculator, our computer, as we start to use those and they get warmer, semiconductors actually produce more electricity or can conduct better electricity at higher temperatures. So this is conduction bands, and just to compare conduction bands for these different items, an insulator has a huge gap between valence band and conduction band. And then you have your Fermi level smack in the middle. And you can read here that the large energy gap between the valence and conduction band says that in ordinary temperatures, no electrons can reach the conduction band. Hence, an insulator. But for semiconductors, you do have a gap that's small enough that thermal energy can bridge the gap for some electrons. And again, using the equation from before, as long as it gets warm enough, this can happen. And then, of course, for a conductor, there's no bridge to gap, so the valence band overlaps the conduction band, and we have complete conduction all the time. But again, we're looking at semiconductors. So, looking at this slide, we see that the valence band will have a little Fermi level to jump across. Now, on the right-hand side, here's what you see with doping. When you have doping, you add extra electron levels, which raises the Fermi level, and so this distance is easier to achieve. And all that does is raise the Fermi level to a point where conduction can be more easily done. And that's what you see with doping. Now, for intrinsic semiconductors like silicon and germanium, the Fermi level is essentially halfway between the valence and conduction bands, okay? And what we have here is the probability of occupation state. So this is using the equation, and this is what we see. This is the probability that we're going to have the electron. This is the availability or number of energy states available. We take these two graphs and put them on top of each other, and what we see is an area is where the conduction band will be met. So this is the energy where the conduction band will be met. So essentially this is what makes a semiconductor work using the Fermi statistics. Why are semiconductors important? Without transistors and integrated circuits made of semiconductors, much of modern life would be very different. No handheld electronic games would entertain children. No barcode readers would speed up checkout lines and compile inventories at the same time. And no computers would handle tasks at work and home. Nor would microprocessors control the operation of cars, planes, and space vehicles.